Welcome, ladies and gentlemen. So let's go ahead and generate the Maclaurin series for a new function, f of x equals cosine of 2x, based on our knowledge of Maclaurin series for a well-known function, cosine of x. So go ahead and share with the class our Maclaurin series for cosine of x. What does that look like? And you can do the first several terms, and then we'll collectively do the summation notation for the series. So what do the first several terms look like for cosine of x, plain Jane? So what does that look like? Danny?
1 minus 1 over 1 minus x squared over 2 factorial.
Awesome.
Plus 1 x to the 4th over 4 factorial.
Great.
Minus.
And then we can go right to the generalized term after we see the pattern, yes? And so we can see that it looks like for our generalized term, we have x raised to the power of, looks like, is that 2, where we start with a counter of index n equals 0, 1, 2, 3, and so on and so forth. And so we've got our even powers for our exponents, right, in ascending order. And then that's all over, looks like 0, 1 times 2 is 2 factorial, 2 times 2 is 4 factorial, so 2n factorial, yes? And so our summation notation would be the sum from n equals 0 to infinity of this generalized nth term x to the 2n over 2n n factorial with a negative 1 here. So we need to go ahead and do that. Look like negative 1 to the n. And let's check and make sure that that would do our signs correctly. N equals 0 would be a positive first term. N equals 1 would be a negative second term. Is that right? Awesome. Okay, so what are we going to do? Well, we're going to generate the Maclaurin series for f of x equals cosine of 2x. So what do we do? Well, it's as simple as substituting right into my input x and replacing it with 2x. So we'll go ahead and say, all right, so if cosine x is given by this series, then cosine of 2x must be given by this series replaced with every input x changing to 2x. So here we go. Still 1 minus, but now it's 2x squared over 2 factorial. Plus, and now it's 2x to the 4th over 4 factorial. Minus. And now it's still negative 1. That doesn't take any x's. Alternating sign. But my generalized term now, my base in this power, x, is replaced with quantity 2x to the 2n all over, and then there's no x here, so that's still 2n factorial. Let's see if we can't write the summation notation for that. So this would be the sum from n equals 0 to infinity of negative 1 to the n. Notice how this becomes 2 to the 2n, x to the 2n. So we'll go ahead and put our 2 there, and that's going to be 2 to the 2n. And then x to the 2n, all over 2n factorial. And let's do a quick check with n equals 2. If n equals 2, right, we should generate this term. So let's see. If we put in n equals 2, we get negative 1. Quantity squared is positive. That's good. So we're checking this term. N equals 2, 2 to the 4th. That would be 2 to the 4th. X to the 4th, all over 2 times 2 is 4 factorial. So it works. So this generalized right term then works in our summation notation as well. So raise your hand if you had either the green line or the red line. Thanks. Sophia?
So whenever you write series or like summation notation, do you have to isolate the x, or can you leave it as 2x?
That's a great question. No, you don't have to isolate the x necessarily. However, if it were multiple choice, you'd have to be able to manipulate it to make it look like one of the answers if yours doesn't appear. So in the textbook answers, we've been seeing a lot of the x manipulated. At least that's what I've been seeing it written. And then I found in my free response from the 2015 practice for BC, I found one that had the parentheses 2x here too. So yes and no. But the key idea is that we're able to manipulate it to recognize equivalent forms. Other questions about one? Yay, chose. All right, let's go ahead and take a look at our second one then. This will be a great kickoff for our discussion today. Generate the third order Maclaurin polynomial for f of x equals sine of x and use it to approximate sine of 0.3. So we know, right, that the Maclaurin series for sine of x is a very common function. Actually, we need to know that for BC too. So we should be able to jump right into our Maclaurin series for sine of x representation. It is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So we're going to have to know that. I know n cosine x and e dx. But those are the big three. The big three transcendental. But we could certainly generate it using derivatives as well. Okay. In the interest of time, I'm going to go ahead and go right to our Maclaurin polynomial. I know that our third order polynomial, because sine of x is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus generalized a to 1 to the, does this work if we do n, and then x to the 2n plus 1 over 2n plus 1 quantity factorial. Does that look like our sine of x Maclaurin polynomial? Now we just want the third order Taylor polynomial, right? Or Maclaurin polynomial centered at, which is Taylor polynomial centered at x equals 0. And so our p sub 3 for a third order Taylor polynomial would just stop at our third derivative, our third degree term. Our third degree term then is x cubed, and so our polynomial ends up just being the first two non-zero terms of that series. That's just x minus x cubed over 3 factorial. Raise your hand if you had this generated for your third order Maclaurin polynomial. Yes? Okay. Great. So then what? Well, we're going to use that third order Taylor polynomial to approximate sine of 0.3. And so, yes, we can use the calculator for that. We know that this evaluated at 0.3 would be 0.3 minus 0.3 cubed over 3 factorial. And we'll be coming back to this later. So we'll get a good decimal for that. But again, we could use our calculator for this. 0.3 minus, how do I want to do this? 0.3 cubed over 3 factorial 6. What's that? 0.2, did I double click it? 0.2955, raise your hand if you got that right. And we get 0.2955, 0.2955. Okay. So we're thinking that the sine of 0.2955, I'm sorry, the sine of 0.3 is about 0.2955. Now we only use the third order Taylor polynomial, right? And so in terms of the accuracy of this approximation, what do you think? How good of approximation do you think this is of sine of 0.3? Well, we used our graphing calculator to generate, right, our approximate value. Let's go ahead and use our graphing calculator in radian mode and just get 0.3 and compare it for right now, and then we'll see how we can bound our error later in today's discussion. And so I just want one of those up here for my screenshot. Radian mode approximation for my calculator built in of sine of 0.3 is 0.2955202. And so it's looking like we're not too shabby. And how far did we go? Okay, how far did we go with our Taylor polynomial, Courtney? Yeah, we only went a third order. And so how could we improve the accuracy of our approximation with Taylor polynomials? Kobe?
Just by increasing how far we go.
Yeah, we could have gone to the 5th order, right? Or the 7th order, or the 9th order, right? Every time we add a non-zero term, we're going to improve this approximation. As you consider the signs of this term, and I'm now jumping a little bit ahead just because I'm so darn excited about our discussion today, but what happens with the next term that we would add to this approximation? Well, we know that the next term would be plus x to the 5th over 5 factorial, and so it would take this approximation, which we got at 0.2955, and it would increase it a little bit, right? because we're plus x to the 5th over. And then what would we do? Well, the next one would be minus x to the 7th over 7 factorial, right? And so that would decrease a little bit, and then increase it, and then decreasing. As you consider the partial sums for these approximations as we continue to add terms, notice how it's honing in on some particular value, right? And that value is the limit as n goes to infinity, which actually ends up being the exact value of sine of 0.3, right? Better than my calculator approximation in radian mode, the exact value as we let the number of terms in that Taylor polynomial increase to infinity. We're going to use that as we go to bound the error today using Taylor's theorem. So this is a super powerful day and a big deal, and I'm pretty excited about it. Tyler?
Do we have to memorize, so in the top right corner, if you wrote the -1 to the end, all that stuff, do we have to memorize that for the test?
You should, because it'll save you time and energy. Now, do you have to? No, you don't have to, because we could certainly have generated the 3rd order or 5th order, right, or 7th order Taylor polynomial for sine of x using the procedure, right, f of 0, f prime of 0, f double prime of 0, and see the pattern. However, that would take longer than if you just memorize. See what I'm saying? So, do you have to? No. But I will say that you should know the common familiar functions for, the familiar Maclaurin series for sine of x, cosine of x, and e to the x. Those are the big 3. And so it's only 3, but those show up time and time again. There's a couple that I was going through the BC practice from 2015, and there were a couple where there were simple substitutions like this. So if you knew this, you could just replace that x with the thing, then you could pick the right thing from the multiple choice in a fraction of the time that it would take to generate it. Could you still generate and get the right answer? Yes. It would just take time, and when the clock is ticking, you want to be as efficient as you can. So it's a trade-off between the time it would take you to memorize that, commit those to memory, versus the time it would take to generate it. Good question. All right. So where does that leave us? Well, let's go ahead and pause that because we're going to use that as our kickoff point. Instead, I'll pause the recording at the same time, and we'll take care of our OTL check. Okay, so we've seen that the nth order Taylor polynomial approximation of a function centered at x equals 0, that is the nth order Maclaurin, right? We've seen that that's given by our value of the function at x equals 0, and then the plus the value of the first derivative at x equals 0 times x, plus the value of the second derivative at x equals 0 over 2 factorial, right, times x dot dot dot, where we're taking the nth order derivative evaluated at my x value where I'm centering my approximation, divided by n factorial, and then times x to the n. So that's how I generate my nth order polynomial. Now, if we generalize that and center my polynomial approximation about any x value, the generalized form then includes my transformation x minus a. And so I'll evaluate my function at x equals a. I'll evaluate my derivatives at x equals a. It's just my power term now is an x to the n. It's x minus a to the n, right? And still over n factorial. This allows us, right, flexibility in where we create our approximation. We can now shift horizontally wherever we want to generate our approximation, and thus make our interval of convergence, when applicable, right, fit right into where we're trying to do our approximation. So the Taylor series then represented by a function. Now, I give you this one, right? So the Taylor series representation then, we'll just go ahead and extend that to the infinite form, and we'll include a generalized form here, n equals 0 to infinity of the nth derivative evaluated at, oh, did I say a? Evaluated at a over n factorial, and then times x minus a to the n. Does that match our earlier observation? Yeah, we've got the nth order derivative evaluated at my centered x value divided by n factorial, and then times my quantity x minus a all to the nth power. When this is centered at x equals 0, then my a value is 0, and we have our Maclaurin series. All right, so this is our starting point today. While there's something innately beautiful about a Taylor series that converges, right, over its interval of convergence, and you saw how when we added successive terms to our approximation for sine of x, more and more of the sine wave was covered exactly. If we continued adding terms, right, more and more ways would be included. In fact, the sine of x Taylor series converges for all real x, the entire number line. We could continue adding terms and cover up the entire sine wave, and that's pretty cool. And while that's pretty cool, it's essentially Taylor polynomials, right, that do all of the work. In fact, even computers have to use finite sums to do all their calculations, right? We can't do that actual infinite series. We can only conceive of how the entire sine wave would be covered as we continue to add terms. And so we saw with our Bellwork that just after a third order polynomial, which only had 2 terms in it, how close we're getting to the actual value, right, or this radian mode predicted value from our calculator of the sine of 0.3, right, when centering our approximation near x equals 0. So how good is good? And that's the subject of our discussion today. We're going to be able to bound the error and tell exactly, guarantee, how close our approximation is based on how many terms or what order polynomial we use for our approximation. It's while the series, right, get the aesthetic beauty, the polynomials do all the work. All right. So write the general form of a function f of x in terms of its nth order Taylor polynomial and generalized remainder. Remainder for you, that is our original function f of x could be given by a sum of 2 parts, where the first part is our Taylor polynomial, right, of degree n, whatever we decided. So if we did a fifth order Taylor polynomial, then it's a p sub 5 of x, and that would go just to the 5th derivative, nx to the 5th, plus then all the other terms, right? This r would be the remainder. And so we can think of this as my original function in all its exactness. In turn, then, is given by our nth order Taylor polynomial. We know how to generate that. We start taking derivatives. We evaluate those derivatives and plug them into my generalized form for the Taylor polynomial, where I take the nth degree term and divide it by n factorial, plus, where we stop, all the other terms. This is the remainder, right? If we stopped at x to the 5th for sine, then r of x would start with x to the 7th over 7 factorial minus x to the 9th, dot, 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 forever. And so this r is referred to as the remainder polynomial. Suppose now that my function, right, and its series representation given by p sub n of x plus r sub n of x, the remainder, suppose that converges for all x on some interval. If this converges for all x on some interval, then as long as we're talking about our x value on the interval, then f of x, the exact value, is given by the sum, right? The exact value is given by the sum of the Taylor polynomial plus whatever remaining terms there are, yes? So if we want to approximate that function using the Taylor polynomial, we can figure out exactly how much we're off by considering the magnitude of that remainder. Whatever we cut off the end, whatever we chunked off the end, that remaining portion is going to represent the error in our approximation of the exact value. So, if f of x is given by f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus the nth order derivative evaluated x of a over n factorial times x minus a to the n, right? That's my, sorry, I'm coming back. That's my blue, right? Nth order Taylor polynomial plus, what do I have left? Well, plus I've got the remainder left. So our nth order Taylor polynomial, right, is just given by that blue expansion. Then whatever nth order I stop it at for my polynomial, whatever is remaining here in red, right, that's my remainder. If f is exact, then the blue is my approximate, and the difference between the blue and the exact, my remainder, that's the error in my approximation. Where r sub n of x is given by that next one. If we kept going, look, if we kept going, what would the next one be given by? It would be given by the next order derivative, that is f of n plus 1 derivative, evaluated at some c, and this is where Taylor's theorem comes in, evaluated at some c in between x and a, so on my interval, right, where we're doing the approximation, over n plus 1 factorial. The next term, I increment my counter by 1, times x minus a to the n plus 1. And so this is the next one on its way. Okay, so what's the error then in my, from an nth order Taylor polynomial approximation of a function? Well, we just saw that. Back to our shorthand notation. There's our Taylor polynomial. Here's my remainder polynomial. The error in my approximation would be the magnitude of the difference, right? The magnitude of the difference between f of x and my Taylor polynomial. So that would be actual minus approximate. And the magnitude of that would be absolute value. And that's given by what? Well, if we solve this, right, if we subtracted over my Taylor polynomial evaluated at the x value from the actual function evaluated at x, what would I be left with? What would this equal? If I subtract over the p, what would this equal?
X would equal Pn of x plus Rn of x.
Right, and so, oh, I meant the top one subtracted over. This error is the absolute value of r sub n of x. So the absolute value of r sub n of x, the remainder function, the absolute value of that is the magnitude of my error. Right? That's the magnitude of my error. And Taylor's theorem says that that error is less than or equal to, in fact, it's actually exactly equal to the next highest derivative, the next order derivative, evaluated at some x equals c value in between where I centered the polynomial x equals a and my x approximation value over n plus 1 factorial, my next term, times x minus a to the n plus 1. The error actually equals that, but typically we don't know where that c value is. So if we can figure out the maximum value of that next derivative and call it n, then we can bound the error. That is, we can figure out the absolute maximum error possible from our approximation, and that's useful because now we know how precise that Taylor polynomial, how good of a job it does, quotation marks. So n here is the maximum value of that n plus 1th derivative attained on that interval between x and a. And sometimes we have to do that through inspection. We typically don't know what c value, right, for some c value in between a, my centered x value where I created the approximation, and x, the particular x value where I'm doing the approximation. So oftentimes through inspection we have to pick a c value that will maximize that potential value of the next derivative, use that, and that will bound our error. Okay, so this looks a little bit crazy upon initial inspection, but in the past 2 class periods you've done this over and over again. You take the nth derivative, right? You evaluate it at my place where I'm centering it. You divide by n factorial, right? And then my power term is just x to the n. And now we've done that to construct polynomials for 2 different class periods. Now all we're doing is we're going to go to the next, right? The next order derivative and the next higher exponent and divide by the next factorial. That quantity is going to be the absolute maximum error from wherever my approximation stopped, right? So that's the big idea behind Taylor's theorem and bounding the error. This is called the Lagrange Error Formula. So we're going to go ahead and add that. And we'll return to it. I'm going to add it here. And then we'll see it again. So this is called the Lagrange Error Formula. And it's one of the ways in which we'll bound the error. This will always work. Also on our interval of convergence, this will always work. What's tricky is figuring out then what C value to use to maximize the value of that next order derivative, right? We're always trying to get the biggest thing so that we're sure our approximation lies within whatever that error bound is. Okay, let's go ahead and take a look at, however, our sine and cosine functions, where we started our discussion today. Our sine and cosine functions, we can actually utilize a simpler error bound, and that's called the alternating series error bound. And so, if a series has the following three properties, that is, the terms alternate in sign, like our generalized series for cosine of x that Tyler was asking about in the beginning, and sine of x for number 2 with our approximation. Notice how those terms alternate in sign. We had that -1 to the nth power. If our terms alternate in sign and decrease in their magnitude, that is, the term values are getting smaller as the order continues to increase. So the terms alternate in sign, they're getting smaller, and the term value approaches 0 as n goes to infinity. Then we can apply the alternating series error bound. That is, the truncation error after n terms, right, wherever we decide to cut off our polynomial approximation, is less than or equal to the absolute value of the very next term. And so in this case, it's easy to bound our error. All we need to do is figure out what the next term in my series would have been after I did the cutting, and that gives an absolute maximum error to my approximation. So this is the easier test. That is, the error is less than or equal to the absolute value of the next term. So that will be easy to tell. And visually, when we talked briefly about our sine function and the partial sums, how the next term was a little bit more positive, and then minus a little bit less negative, and then plus a little bit less than that positive, and then we were oscillating back and forth to the true value, right? That's why this works, because that next term is actually the biggest step that you'd ever take, right? After that, guaranteeing that the value of our approximation is less than or equal to that very next step. That's pretty cool. So this is the easier one, and that's for you printables. All right, so now back to our earlier approximation of sine of 0.3. What is the maximum error in our approximation? So let's consider our earlier approximation of sine of 0.3. We did that using our third order Maclaurin polynomial. I'll still call it p sub 3 of x. And we used 1x to the first minus x cubed over 3 factorial. When we did that, we produced the approximate value of 0.2955. Consider this series for a moment and the expansion for sine of x. My nth order polynomial, does it alternate in sign? So yes, so I alternate in sign. Does the size of the term, right, does the magnitude of the terms decrease as the order increases? Yeah, because the next term would be 0.3 to the 5th, right, over 5 factorial. 0.3 multiplied by itself over and over again and gets smaller and smaller and smaller. 5 factorial on the bottom, right, is a larger and larger denominator, so the term values decrease in magnitude. And the limit of the terms as n goes to infinity is 0. So the terms approach 0 as a limit. Check, check, check. If we satisfy the 3 prereqs, then we know the alternating series error bound can be applied and guarantees that the error in my nth order approximation is less than or equal to the size of the next term, that very first term that we cut off. So we know by the alternating series error bound that my error is at most, right, less than or equal to the magnitude of the very next term, that is a sub n plus 1. So all I need to do is go to my original approximation. We stopped at the 3rd order. What would be the next term? Yeah, the 5th order. And so that would equal x to the 5th over 5 factorial. And we were evaluating this at, now this is nice notation. We've got absolute value bars, we're going to evaluate at 0.3. Guaranteeing that my error is less than or equal to 0.3 to the 5th over 5 factorial. Pretty print. Can't live with it. Can't live without it. I get it? Finally? Oh! So what's that say? I don't know. Let's see what that is. So that's 0.1, 2, 3, 4, 2, 0, 2, 5. And we got 0.2955 minus 0.29552020067, which is, so how do we do? This is absolute value of that. Sorry. So how do we do? Is 2.0206 times 10 to the negative 5th less than or equal to 2.025? Yes, it is. And so, right, our approximation was actually a lot better, right, than, I mean, given that we're going over 4 decimal places, but it was better than, right, my absolute error prediction. And so we bounded the error. We know that at most my approximation, right, will be less than this far away from whatever I get from my predicted value. Okay. That's pretty cool. Now, do we always have alternating series? No. And so we have to be able to use the more complicated Lagrange Error Formula as well. So let's compare this error bound with our predicted. We did that. And we'll go ahead and do one graph because one of your OTL exercises, we're going to have you check that out too. Okay, so this is kind of a cool technique. Let's go to our grapher. And in our grapher, in y1, let's go ahead and do our exact function. That's our f of x where we started our discussion today. That will be our exact original. And so for us, that was sine of x. Now let's go ahead and use our Taylor polynomial approximation. We did the 3rd order. And so for us, the 3rd order polynomial was what? In y2, we'll do x minus x cubed over 3 factorial. Yes? Okay. Now what we're going to do is we're going to graph our error function. Our error function, r of n, right? R sub n of x, what's that? Well, we saw we could subtract over my Taylor polynomial from my original, right? Take the absolute value of that, and that was my error, the magnitude of my error. So what we're going to do, we're going to do math num abs for absolute value. And we're going to do y sub 1 original f of x exact minus y sub 2 nth order Taylor polynomial. So I want bars, y bars, function y1 minus bars, y bars, function y2. And now I'm going to go ahead and turn off the graphs of y1 and y2, okay, because I'm going to restrict my window. So I'm going to highlight the equal sign and press enter to toggle off those graphs. I only want this third one produced. And I'm going to go ahead and specify my window and make it very small so I can see how my polynomial approximation matches the function when I'm close to my centered x value from which it was created versus as I get towards those edges. And so what do I want to do? Well, we were approximating around, what were we doing? Around 0.3, right? We're doing around 0.3. And so I'm going to go from negative 0.5 to positive 0.5 for my x's, because we centered it was a Maclaurin polynomial, wasn't it? So it's centered at x equals 0, so I'm going to center that. How's that? And now for my y window, I'm going to use my error. I know that my absolute highest error from this approximation, in accordance with the alternating series error bound, was 0.00002025. So guess what? For my y min, I'm going to do 0, and for my y max, I'm going to do 2.025 times 10 to the, was that 5, do we say? Negative 5? So I'm going to go ahead and set my window so that my y max is my maximum error attained. When we graph y sub 3, right, when we graph y sub 3, we should, right, see my error go to 0 in the middle of my graph, right? It shouldn't have any height because there shouldn't be any error at x equals 0. That's where I instructed my thing. But as my x values get farther away, like when we went to 0.3, then we should start seeing some error. So let's go ahead and see if my picture is beneath my predicted maximums. And if I were to trace 0.3, voila, it looks like it's less than, just barely, right? It's less than my maximum error for my alternating error series test, right? It's less than the 2.025 that my alternating series gave us. And so what is this picture we're looking at? That is the funniest looking sine graph I've ever seen. No. This is the error in my third order Taylor polynomial, right? Prediction centered about x equals 0. And look at, there's no error when we're at x equals 0. There's minimal error, but look at, this is still 0.00002025. See what I'm saying? And so this is still very small rocks. But we can visually see that our error increases as we move farther away from our centered x value. You guys see? Okay. Yeah, I want that. Cool. All right. So sometimes we don't have an alternating series, in which case we can't apply the alternating series error bound. However, the Lagrange Error Formula comes directly from Taylor's theorem and says that the exact error in my polynomial approximation of degree n is given by the next derivative evaluated at some x equals c divided by the next factorial and then times x minus a to the n plus 1. So basically the next term with a multiplier of the maximum derivative value attained for some x equals c in between a, where I centered my approximation, and x, the x value we're approximating. for some c in between x and a. And while that may or may not be useful, right, we typically don't know what c value that is, we can then choose a c value that maximizes the value of that next derivative to bound the error, thereby ensuring that we know our approximation is less than or equal to that maximum error possible. So we're actually going to be able to choose some c value on my interval there to maximize that value of the next derivative, thus ensuring that our approximation is within some absolute maximum error possible. All right, we're going to hold off on our factorial discussion. We did a great comparison earlier, right, talking about rates of change and relative growth rates of functions, and we saw, well, while we're here, we saw, I didn't include it for the pronouns, but we saw how if we ordered the rates of growth for positive as x gets big, how would we order these right here? Well, I can grab onto the big two right away. How do exponential and power compare? Right? How do exponential and power compare? In the long run, as x goes to infinity. Who grows quickest? Exponential. So exponential outstrips power growth, right? If I'm looking to x very large, exponential always wins. We see that power functions, right, when we're talking about positive n, as n gets larger and larger, x to the n, definitely bigger than linear, which is just x to the first. And logarithmic, the inverse of exponential, that's bringing up the rear. In fact, logarithmic functions then grow more slowly than linear. All we need really for today's discussion is that new introduction. The new introduction of that term we've been dealing with is factorial growth. And what I wanted you to get out of our earlier discussion back in Unit 4 was that exponential is the big dog and outstrips power growth, is that now factorial supplants exponential growth as the big dog. Factorial growth will outstrip exponential growth so long as you look to the very large. And so what are we going to do for factorial? We're going to add that to our discussion and now make logarithmic. Linear grows more quickly than logarithmic. Power grows more quickly than linear, exponential. And then factorial growth now outstrips exponential. So we got a new winner. In fact, wouldn't it be cool if I put factorial growth is the victor now as we let x get large. We'll eventually outstrip exponential growth. The reason we needed that is to set up for our convergence discussion later. As you consider the remainder, right? The remainder, that is the error represented in my Taylor polynomial approximation. As n gets very, very large, right? If we can show that my remainder, my error, goes to 0, then I know my Taylor polynomial, Taylor series converges, right, for all x in my interval. So the idea is that if my remainder shrinks to 0, then I'm left with the exact function. That is possible because factorial growth on the bottom grows more quickly than our power growth or our exponential from that first term for our derivative. So let's see. All right, so that. Let's, don't have one for that. Okay, so we're going to go ahead and take a look at a couple different functions together. We're going to vary our centered, our value, x equals a, to practice. And then we're going to go ahead and bound our error. We're going to bound our error over the interval using either the alternating series test or the Lagrange Error Formula, okay, depending upon what our Taylor polynomial looks like. So let's go ahead and use the function f of x equals cosine of x. We're going to center our Taylor polynomial about x equals pi over 3. And we're going to do a fourth order Taylor polynomial. So we can use our generalized form, but we're going to have to generate this not about x equals 0, but about x equals pi over 3. So does that change things for us? It does, because we're not doing f of 0, f prime of 0, f double prime of 0, which was very nice. When we did that, right, our oscillating behavior of the derivative, sine to cosine, right, to negative sine to negative cosine, had every other one equal 0. When I evaluate my derivatives at pi over 3, will I get those 0 terms? No. So we have to generate by hand. Let's go ahead and do that. We still need the same things, right? We've got our f of pi over 3. We need f prime of pi over 3. F double prime, F triple prime, and we wanted to go to fourth order or fourth derivative. All right, let's go ahead and do it. So f of pi over 3 would be my original cosine of x evaluated at pi over 3, and that is what? I'll do it. Oh, come on. Oh, almost. Yeah. Is that so the pi over 6 to the further x coordinate, so the shorter as the 1/2? Yes, the 1/2. F prime of pi over 3 is gained by evaluating the first derivative at x equals pi over 3. The first derivative of cosine is opposite of sine of x. Evaluate at pi over 3. Danny's ready for this one. So then the sine at pi over 3 would be, and then opposite of that would be negative root 3 over 2 for my value of f prime of pi over 3, yes? Is that right? So pi over 3, sine is root 3 over 2 times the negative in front. Yes? Double derivative. What? Double derivative? Guys, double down on all that. So when I differentiate negative sine of x, that goes to negative cosine of x, evaluate pi over 3. And now we're back to our 1/2 times the negative is negative 1/2. F triple prime, the derivative of negative cosine, right, is going to be back to positive sine, right? Positive sine of x. Evaluated at pi over 3 equals root 3 over 2 positive. And lastly, our fourth order derivative would be the derivative of sine of x is cosine of x. Evaluate at pi over 3. And we've come full unit circle. Oh, and we're back to positive 1/2. Yes? Okay, so how are those function and derivative values helpful? They provide part of the coefficients on my power terms, but not all the coefficients. What do I still need to do? I still need those factorials, right? So this will be divided by 1 factorial is 1. This will be divided by 2 factorial, 3 factorial. And my power term won't be x to the first, x to the second, x to the third. It'll be what? Quantity x minus pi over 3 to the first. Quantity to the, and so on. All right, let's do it. So my fourth order Taylor polynomial centered at x equals pi over 3 is given by f of pi over 3 is 1/2 minus root 3 over 2 quantity x minus pi over 3 to the first minus 1/2 quantity x minus pi over 3 squared over 2 factorial. Where are we? Right here. Third order. Plus root 3 over 2 quantity x minus pi over 3 to the third over 3 factorial. 1 to go. Plus 1/2 quantity x minus pi over 3 to the fourth over 4 factorial. Yes? What do we do? So there is our fourth order Taylor polynomial, right, for the function cosine of x centered at x equals pi over 3. So this is what we generated. We saw how good of a job my third order sine function did, this is going to even do better because look at more non-zero terms. Okay, I'm hoping it does a better job. Okay, so what do we need to do? Well, we wanted to use error bounds to estimate the accuracy that this polynomial function gives for approximating cosine of x on the interval 0 to 2 pi over 3. Firstly, do we have an alternating series? Does this series alternate? Positive, negative, negative, positive, positive. So no, right? Yes, the signs change, but it's not an alternating series. It's not a negative 1 to the end. Okay, and so we can't use the easy one, which means we have to do what? We have to use the Lagrange Error Formula. But that's okay. The Lagrange Error Formula tells us the exact error. Right? The exact error in this polynomial approximation is given by, I have space here, where do I have this? I don't have space. Let me do this. Since we don't have an alternating series, we can't apply the alternating series error bound, which says that the magnitude of the error is less than or equal to the value of the next term, right? So what do we have to do? We have to use the Lagrange Error Formula, which says that the error is actually equal to the next order derivative, right? What would the next order, the magnitude, I said the absolute value of, what would be the next order derivative? Or where do we stop? So the error would actually equal the fifth derivative evaluated at some c value over 5 factorial times x minus pi over 3 to the fifth. The only problem is we don't know what c is, other than it's in between where I centered it, and I centered it at x equals pi over 3, right? And whatever value of x I'm going to approximate. We're going to do our approximation anywhere from 0 to 2 pi over 3. So what I want you to do is to consider the value of the derivative for an x value in between 0 and 2 pi over 3. We don't know what c value to use to make that error equal it, but if we can choose the maximum value of that fifth derivative attainable on my interval, call it m, then we can bound the error and know for certain that error is guaranteed to be less than that maximum next derivative value times the fifth order term, x minus pi over 3 to the fifth over 5 factorial. And that's the Lagrange form, error bound. As simple as I can get it. All right, so what are we going to do? Well, let's consider what interval we're talking about. We're talking about the interval from 0 to 2 pi over 3. We need to find the maximum next fifth derivative value produced on that interval. Use that, and then we know our error is guaranteed to be less than or equal to that. So what do we need? We need our fifth order derivative. So back to our fourth order derivative. Our fourth order derivative was what? Cosine of x. Therefore, our fifth derivative is the derivative of cosine of x, which is opposite of sine of x, evaluated at some c value. Okay? Sine of x, right, evaluated at some c value such that c is chosen in between my centered x value, which was pi over 3, and my bounds on the end was 0 and 2 pi over 3, did we say? 0 and 2 pi over 3? So everybody spin with me. We're trying to find the maximum, right, the maximum derivative value producible, which means we need the largest value of sine, right? The largest value of the sine produced on the interval 0 to 2 pi over 3. So let's start spinning. What's the value of sine of 0? 0. pi over 3 is where I centered it. The sign there is pi over 2 on my interval. What's the value sign there? Stop at 2 pi over 3. That's the end of my interval. What's the value sign there? So what's the maximum value of sine, my fifth derivative, achieved for any x equals c value on my interval 0 to 2 pi over 3? 1. Isn't the sine at a maximum, the y-coordinate is at a maximum at the top of my unit circle there at pi over 2? Therefore, we're going to choose c to be pi over 2 to guarantee our error, right, is less than or equal to that. So we chose c to produce the maximum value of the next order derivative, therefore bounding my error with certainty. So we're choosing c to be what? Pi over 2. Then we know that the absolute value of the fifth order derivative opposite sine of pi over 2 is absolute value of -1, which is 1. So m equals what? 1. Which means my error is less than or equal to the absolute value of x minus pi over 3 to the fifth over 5 factorial. All right? We're almost to a number. I need to ensure my approximation holds for all x values in between and including 0 to 2 pi over 3. So now consider this power function. When is this power function at a maximum? Well, I can let x be 0. If x were 0, then 0 minus pi over 3 would be negative pi over 3 to the fifth, right? If x were 2 pi over 3 minus pi over 3 would be 1 pi over 3, x to the fifth. And I'm going to take the absolute value either way. If I choose anything in between, then this quantity shrinks, right? The difference between pi over 2 and pi over 3, right? Pi over 12, that shrinks. So this quantity is at a maximum on the ends of my interval in this case. Therefore, my absolute maximum error attainable would be either 2 pi over 3 in here or 0 in here, right? Is going to ensure that the maximum error experience would be pi over 3 to the fifth all over 5 factorial and the absolute value of that. Oh, the moment we've been waiting for. Can we do it? Can I write a check? Yes. I don't need to do my bars because I'm making that positive right now. And pi over 3 to the fifth. Over 5 factorial. Math. 4. 0.0104945022, which isn't so good, but I get my actual error is going to be less than that. I just know that it's going to be, right? It has to be less than that. Can we pick an x value on that interval to c? We could, and that would be until plugging in. I think I want to try to do one more. I'm going to hold off on that and say we know that our approximation anywhere on that interval, which is a pretty big interval in fairness, has to be less than that. Right? It has to be less than that. Okay. So do we want to do this one or do we want to do?
We don't have room.
What?
We're out of room.
Oh, who picked medium? We got large.
I got large.
And yes, all right. All right, we've got one more. You guys want to do the exponential, e to the x squared, or would you like to do the power, x to the 3/4? Power? Okay, let's go ahead and do the power. Oh, you guys. Let's go ahead and use error bounds to estimate the accuracy of the approximation of the third order polynomial for f centered about x equals 16. Okay, so let's go ahead and first generate our third order. Thank goodness we're only doing 3. Our third order Taylor polynomial for f of x equals x to the 3/4. What do we need? Well, we're centering it about x equals 16. Therefore, we need f of 16. We need f prime of 16. We need f double prime of 16. And we wanted third order, so we need f triple prime as our final derivative needed for our third order polynomial. All right, so f of 16, go to my original. 4 through to 16 is 2, to the third is 8, so I'm getting 8. Are you guys getting 8? F prime is given by exponent times the base raised to 1 less. And that's 3x to the negative 1/4, yes? And 16 to the 1/4 is 2 times 4 on bottom is 8 is 3/8. You guys get 3/8 for f prime of 16? Cool. F double prime is negative 1/4 times 3/4 is negative 3/16 x to the negative 5/4 equals negative 3 over 16x to the 5/4 and 16 in for x, the 4th root is 2 to the 5th is 32. 32 times 16 is a lot underneath negative 3. So I get negative 3 over 512. Yes? One to go. F triple prime is negative 5/4 times negative 3/16 is positive 15/64 x to the negative 9/4 equals 15 over 64 x to the 9/4 evaluated at 16 equals 2 to the 9th times 64 underneath 15. What's that? 32,768. 32,768?
Yeah.
I remember that. I remember 6,075, but anyway. Anybody else get that? Yeah! All right. So what does that do for us? Well, that tells us part of the coefficients. We still need to draw our factorials. Let's do it. So my third order polynomial, call it p sub 3 of x, is given by f of 16. That is 8 plus 3/8 quantity x minus 16 to the first minus 3 over 512 quantity x minus 16 squared over 2 factorial. Yes? Plus 15 over 32, 7, 6, 8, quantity x minus 16 to the third over 3 factorial. Oh. All right. Whew. Oh gosh. Okay. Do we have an alternating series? No, we don't, or do we? Can we say that we do?
Yes.
If we start counting at f prime, that 8, right, once it's accounted for, does that, right, in my sum, does that affect the alternating series? Well, what if I just took off the 8 from the value of this sum, right? And looked at these next terms, 3/8 minus plus, will the next one be positive or negative? How do you know? Will the next one be positive or negative? Positive. And so if we were to start our counting here, right, do we have an alternating, that plus 8 is just like it's a real number, plus 8. We could add that on. We could consider the limit then of these terms here. Now, do the terms decrease in magnitude? They do. Right? For my approximations, do these terms decrease in magnitude? Yeah, look at those fractional values. You see the 3/8, the 5/12. This term, however, is getting larger, right? But it's doing so as a power. And my interval, 15 to 17, ensures that this value being raised to the exponent is going to be in between what? -1 and 1, right? Ensuring that this, at its maximum, will only be 1. Which means my factorial will overwhelm and my terms will decrease in magnitude, yes? So we've got, starting here, alternating series, decrease in magnitude, and is the limit of the nth term 0 as n goes to infinity? Yeah, this term must go to 0 as n goes to infinity, as we've seen with our coefficient and our factorial growth. Therefore, our alternating series bound. Can I go to the next one? Where do I go to the next one? Our alternating series bound guarantees what? Guarantees that our error will be at most less than or equal to the magnitude of the next term, right where we truncated it. Where did we truncate it? We truncated it at the third order. So what do we need? We need the fourth term. Can we get the fourth term? Yes. Let's go back to my third derivative, 15/64 x to the -9/4. Help me out. 15/64 x to the negative, what was it? Was it -9/4? So the derivative of that would be the next derivative would equal yes? You got what, 16? Awesome. Which then is 2 to the 13th. Which is very big. And the -135. Did you do this?
Times 256 is 2,097,152. So times 35.
152? Everybody else get this? Yes? What does this tell us? This is the value of the derivative at x equals 16, right? So we still need that over what order? Fourth order? 4 factorial? And x minus 16 to the fourth? And what interval are we talking about? 15 to 17, right? We're talking about from 15 to 17. Any x value in 15 to 17 is going to make this base in my power in between 1 and what? Negative 1 and 1, which has its maximum magnitude when it's 1, right? So this is just 1. So the maximum error experienced is 1 times this over that times that, which is very small. So I'm getting the magnitude of that is absolute value of, which is 135 over that times 4 factorial, which is very small rocks. And we could get a decimal for that. Okay. Great.
Wait, how did you choose what to put in for x?
Great question. We wanted this approximation to work for any x value on the window 15 to 17. So it could be any x value from 15, 15.001, all the way up until 17. So what I considered is what value of x would maximize this error so that I ensured my error would be less than or equal to it. So I would do it for whatever x I was approximating, that's the x I would use. But because we weren't given a particular x, like in the Bellwork, what's sine of 0.3? We were said, how well will this approximation work over this entire interval? I said, what could I pick from this interval that would maximize the error? Now I know everything else is going to be less than that error. That's what I did. I considered the original window. All right, let's close it up. So we need the general formula for a function f in terms of its nth order polynomial and generalized remainder, and you can just use p's and f's and r's. And you go with 3 terms. Which term represents the error in using a Taylor polynomial to approximate a function? What 3 requirements are necessary to apply the alternating series error bound? If those prerequisites are met, what does the alternating series error bound tell you about the error of the nth order Taylor polynomial approximation of the function? And lastly, what's the Lagrange error formula tell us about the error of that same nth order Taylor polynomial approximation? I'm going to pause the recording and give you a minute to write those down. Okay, so the general form of my exact function f of x, right, in terms of its nth order Taylor polynomial, is f of x equals my nth order Taylor polynomial approximation plus r sub n of x, that is the remainder function, right, whatever's left over. Which term represents the error? That's the magnitude of my remainder function, right? That represents the error. What 3 requirements do we need? Well, we need, right, to have an alternating series, so we must alternate the sign. So my terms alternate in sign. My terms have to be doing what? Getting smaller, so they decrease in magnitude. And their limit has to be to 0, so the nth term goes to 0 as the limit. If they're above requirements are met, then what happens? Then we know my error is at most the magnitude of the next term. Call it a sub n plus 1. So all I have to do is figure out what the next term is, and that's the maximum error attainable. My approximation is going to be less than that. What does the Lagrange error formula tell us about us? It says that the error is exactly equal to the value of the next derivative. That's the n plus 1th derivative at some x equals c value on my interval in between the point of creation and the x value that I'm approximating over n plus 1 factorial times my quantity x minus a to the n plus 1. Typically, I don't know what c is, and so instead what I'll do is I'll make this a less than or equal to, and then choose a c that maximizes the value of the next derivative. therefore ensuring that my error will be less than or equal to this term. You guys are awesome. I'm going to put the OTL up next hour, okay? So I don't have it yet. I'm going to modify it based on our discussion today. Please check Moodle to get updated OTL information.
Someone screen